Well, good afternoon, everyone, and thank you for joining us. My name is Chris Vonamy. I'm the Deputy Director for the DuPage County Stormwater Management Department, and we are here for a water quality outreach webinar where we will learn about the Bee Slough combined sewer overflow project in Evansville, Indiana. The project utilizes treatment wetlands and recirculation pumping stations to treat combined sewer overflows. This project is part of an environmental stewardship program instituted by the Evansville Water and Sewer Utility to utilize green infrastructure and best management practices to prevent pollution and improve water quality. This is a free webinar, and one professional development hour will be made available for your participation. We have several of these lunch and learn webinars throughout the year. We find they're a great way to connect like-minded individuals and organizations who are concerned about the water quality in our local lakes, rivers, and streams. These workshops are part of our public outreach and education programs and help us meet our permit requirements as outlined by the Illinois Environmental Protection Agency. The webinar is being recorded, so if you know of others who couldn't be with us today and might benefit from this information, we will make a link to the recorded presentation available shortly following the webinar. Just before we begin, a couple quick thank yous. Thank you to Raul Galvin. He's our Stormwater Outreach Coordinator, as well as Mary Beth Falsey. She is our Water Quality Supervisor, and they set up this webinar and lined up our speakers for today. And speaking of our speakers, thank you to Daria Uwama-Ora and Amanda White, who are both engineers with Greeley and Hansen and are going to be teaching us and telling us about this Bee Slough project. And then finally, I'd also like to thank again all of you for joining us this afternoon. Before we get started, I just wanted to point out, I know everyone knows this, it is summer, and that means it's vacation season. My family usually goes on vacation every summer with my extended family, including my parents and sisters, brother-in-laws, nieces and nephews. And we usually drive down to Gulf Shores, Alabama, and stay in a big beach house right on the water with my entire family. We actually just got back. We had a lot of fun. And one of the fun things about the trip is the drive down, because we all drive down together in one big convoy. And sometimes with such a long drive, I get worried about the price of gas, but it really wasn't too bad this year, especially the further south that we got. We actually stopped in a small town in Alabama, and I got gas for only $1.99, which was pretty incredible. Unfortunately, it was from a Taco Bell. Anyway, my point is that I hope everyone can find some time to get away, be with family, friends, just by yourself, to rest, relax, enjoy nature, and do the things that you like to do. All right, I better turn things over to Daria and Amanda, but before I do, I want to remind everyone that you're muted. If you do have comments or questions during the presentation, please type those directly into the chat box, and we will relay those on to our speakers at the end of their presentation. I think that's it. So let me introduce our speakers. First, we have Daria Uwama-Ora. She is a project engineer at Greeley and Hansen with 6 years of experience in water and wastewater utilities engineering and construction. She received a Bachelor of Science in Civil Engineering from the University of Colorado at Denver and a Master of Engineering from the University of Florida with a concentration in engineering project management and water resources. Her experience includes pipeline design and water and sewer systems, distribution system hydraulic modeling, field inspection services, and providing office services during construction. Her role for the Bee Slough project included hydraulic modeling of the system, designing and sizing yard piping and appurtenances, and design of the ultraviolet disinfection. Next, we have Amanda White. Amanda is a civil and sanitary engineer at Greeley and Hansen with 6 years of experience in the fields of water, wastewater, and stormwater engineering. She received her bachelor degree in environmental and ecological engineering from Purdue University and is a registered professional engineer in Indiana. Her role for the Bee Slough project includes design of the ultraviolet disinfection, influent screening, influent and effluent pumping, and assistance with hydraulics and the chemically enhanced primary clarification. So that's it. Thank you guys for being here with us. Raul, let's turn things over to Daria so she can start the presentation.
All right, thank you so much, Chris. Hi, everyone. Thank you for being here today. So as Chris mentioned, we are going to be talking to you today about the Bee Slough project. So starting off with the agenda. So we'll talk a little bit about the purpose, and then we're going to cover on a high level wetland treatment and the different types of wetlands that you can encounter out there. We will go in depth with a case study, the project that we did in Evansville. We'll cover the original concept and how we revised the concept in order to optimize the project. And then we will conclude with questions and discussion with everyone. So in a nutshell, the purpose of this presentation is to help you learn more about using wetland treatment as an application for wet weather management. And as an example, we'll go over how we apply this technology to the CSO management in the Evansville project. So starting off with what wetland treatment is, which can also be called constructed wetlands. They are a man-made version of natural wetlands, and they essentially provide a natural way of improving water quality through biological processes within the wetlands. So the plants and bugs basically do the majority of work. There are different types of wetlands you can find out there. You can find free water surface, subsurface horizontal, floating islands, and subsurface vertical flow. So here we'll cover on a high level, pretty much like what each of the types I just mentioned are. So starting off with the free water surface wetland. So these types of wetlands typically have the water surface exposed to the atmosphere. They enhance the habitat for wildlife and can also be used for public recreation by adding things such as trails for hiking. You can have parks, and that way the community is involved with that application. The plants in these types of wetlands are planted based on the location as well as velocities in the flow of water. And as you can see, the flow will typically come in and exit at the same elevation, just a different location. And then one big thing to note with this type of wetland is that you can have issues with odor as well as like bug problems because the water surface is so exposed. And then the next type, the subsurface horizontal, with this type of wetland, the flow is loaded and distributed at the top, and then it exits at the bottom of the wetland. So you can see from the left-hand side there that it's inflowing from the top and then exiting on the right-hand side at the bottom. This type of wetland allows for a permanent pool of water for the vegetation, and this is good for the anaerobic digestion. There are a few issues with this type of wetland. You can have algae clogging, and then this type of wetland is also usually not the best in cold weather environments. And then the next one, the floating island. So this type of wetland, it's a floating island, as in the name. The plants are typically anchored to the sides. The water surface is exposed, similar to the free water surface. The root system of the plants grows deep. It goes like deep to the bottom of the water. And then you'll have like columns of roots, and you usually have like a slimy layer growing within the roots. And that's the biofilm, which it's good for like all of the nice cleaning and like water quality that's happening in the wetland. And then lastly, the subsurface vertical flow wetland. And this is actually the one that we ended up applying to the Evansville Bee Slough project. This type of wetland is similar to the subsurface horizontal flow wetland, except you have the flows flowing vertically. The water to be treated comes at the bottom of the wetland, and then it exits also at the bottom. So you can see there on the right-hand side, influent is at the bottom, and then effluent is also at the bottom on the right-hand side. In our case study, we had perforated pipes running within the wetland to allow the water to exit vertically and flow upwards into the plant system for the digestion to occur. And then one good thing to note here is that because the water comes and exits low and it's not as exposed to the surface, you have less to worry about the smells and bugs. And you end up getting a permanent pool for the plants, which is good, for example, in dry seasons. And then lastly, another thing to note is that this type of wetland might need pumping depending on your topography. So something to note there. And then lastly, the role of plants with wetlands. So as you've seen, we need plants in like all 4 types that I mentioned up there. They do have a big role to play. They are important in allowing the biofilm to grow, creating safe habitat for wildlife, and also in helping in the treatment process, and as well as like providing oxygenation. Okay, so now getting into the case study, we'll talk about how we incorporated the wetlands into our case. So starting off with Evansville. So the site project is located off of the Ohio River, just southwest of Indianapolis. The population is about 160,000 persons. They are still in a city with combined sewer system, and this project really began because they entered into a federal consent decree in June of 2011. And within the decree, they had several requirements related to treating and managing their CSOs and we'll talk about those requirements later on in the presentation. But on a high level, several CSOs discharge into the Bee Slough channel, and that eventually goes into the Ohio River. So just to give you a little bit of background with what Bee Slough is. So Bee Slough is a concrete lined channel where 3 CSOs discharge into it, and then eventually like this discharge after treatment goes into the Ohio River. Now, one problem we had, or the problem they're having, is that the CSOs can sometimes sit in the channel for too long just because you can't discharge into the Ohio River when it's at a high water level. So this goes into why we were working on this project. So this slide shows you the original idea and just kind of like how the processes were set up. Like we have the wetlands there. There's a pump station in the middle. You can see the Bee Slough channel is there on the right-hand side of the project site area. So initially the project was designed to have a 300 MGD pump station, and the end goal was to have no untreated discharges coming from all 3 CSOs. The plan required conveyance, pumping, wetlands, treatment, and disinfection, and with an end goal of meeting NPDES permit limits, and the consent decree requirements as well. So the original plan called for a 300 mgd pump station, as I mentioned previously. The client was looking to get additional analysis, and this is where Greeley and Hansen came in. As you can see, we did analysis of costs. We looked at different parameters to make the pump station smaller, which would mean the project would cost less. So we looked at storage, conveyance within the site area in order to minimize the size of the pump station. So here you see the first iteration of our design, and just kind of how we laid everything differently. So we still had a wetland, and we actually brought the pump station and all the treatment equipment near the east wastewater treatment plant, just in a way to like extend their their treatment plant, sorry, and make it easy for the utility to manage everything. Okay, so getting into the proof of concept. So starting off with the consent decree requirements. So essentially the first one was, to not have any untreated discharges from the CSOs. The wetlands would need to meet NPDES permit limit requirements for water quality. We would need a 59 million gallon wetland for storage. The UV discharge needed to be by gravity at the 100-year flood elevation. And then lastly, we had to ensure that we were not creating any backup into basements. Okay, so we began by evaluating how much storage could be added and how much available space we had for the storage in order to downsize from the 300 mgd pump station. And as you can see, we're able to get quite a lot of storage just on the opposite side of the site area. We got at least 12 million gallons of storage just on the opposite side of the site area, which is good because this meant we could downsize the pump station. So to begin looking at how we could size the pump station, we looked at storm frequencies to size the pump station. We wanted to size a pump station that will be able to be used more than just a couple times of the year. So the pump station would be used even with smaller events. So we checked frequencies of smaller storms to ensure the pump station would be used more frequently. So you can see there the alternatives on the side with every alternative. So with higher storage, a smaller pump station, and on the left-hand side there's the different frequencies for individual storms. And then we did a cost comparison to check storage versus pump station capacity. And we looked at the present costs, like all of the future costs for the utilities and like maintenance and similar stuff. And really we ended up landing between 130 and 100 mgd pump station. So then getting into the recommended concept, this is a snapshot of our recommended concept, pretty similar to the one we saw before. As you can see, we laid out storage on the right-hand side of the facilities there. We have the wetland, the pump stations. We actually started off with a combined influent and effluent pumping station. And then you have the clarifiers there, the UV facility. Okay, now getting into the proof of concept. So while refining the design, we had to keep in mind again to discharge by gravity at the 100-year flood elevation. making sure that our wetlands had 59 million gallons of storage, and then also ensuring that we weren't creating any basement backups. So we did start off by creating a hydraulic profile of the entire system to confirm no basement backups there. So as you can see, we laid out the whole facility system with the pumps and the wetlands, the UV there on the left-hand side. So here you can see this is a different iteration of the pump station there. And this shows the 115 MGD pumping station, which is what we're going to continue talking about. So we were able to finalize the design with 11.9 million gallons of storage. And with the storage, one thing that's really cool, we actually designed it to where you wouldn't have to wait for all of the different storage areas to completely fill up in order to send water to the pump station. So this is what this picture shows. We had different structures with weirs at every storage location. And then another thing to note, so with the design, which this will also go into construction, and there are different constraints we found with existing utilities, specifically under Veterans Memorial Parkway. There's that 108-inch diameter CSO there that we had to kind of work around with our design. And now I think this is when I pass it on to Amanda to discuss a little bit more about the different parts of the treatment plant.
Thank you, Daria. So we talked a little bit about influent pumping. We were looking at our storm frequencies and basically when and how often the pump station would be used. So a couple of things we took another look at. Some of these histograms should look fairly familiar. The ones on the right, we were looking at the 130 MGD and the 100 MGD, so we settled on the 115. And we knew that about 21.6% of our storms were in that 1 to 10 MGD range, with the remaining roughly 80%, anywhere from 10, but really 20 to 120 or 115 MGD. And then so from there, we looked at our 1 to 10 MGD peak flow events, which happen to be the same for our 130 and 100 MGD scenario. So we knew we had quite a few smaller storms and then we had quite a few larger storms. So something else that played into the influent pumping station is the CSOs. So we know we had the 3 CSOs. The depths of the inverts of those CSOs differed. They weren't really all the same as we kind of noted in the previous slides. They had quite a bit different flow rates coming from each CSO. And we also have different construction phasing, as that was starting to be shown in the previous slides. So those overall kind of showed us we might be looking more towards 2 influent pump stations, one for the smaller and one for the larger. The one for the smaller, we chose to be deeper, and then the one for the larger event chose to be shallow, just to get some of those smaller storms and to cover the deepest CSO, and then cover the remaining 85 MGD at our higher elevation. So we had 2 pump stations, the 30 MGD, which would be the first of the 2 to be constructed, and then 85 MGD would be the second pump station. So our phase 1, our first pump station, the size for 30 MGD, we looked at 15 MGD vertical turbine solid handling pumps. basically the third for redundancy. We chose all of our pumps, both 30 MGD and 85 MGD pump station, based on a triple bottom line analysis. We looked at what the operation cost would be, also based on the depth, what kind of is our best scenario. An example of this is we looked at screw pumps for our 30 MGD pump station, but it would be a 2-stage pump, which in that case, it pushes into looking at other different types of pumps. And so the second pump station would be a little bit higher in elevation. There was no need to put both screen and pump stations at that lower elevation. The lower one can get some of the up to 30 MGD in storms, and then anything beyond that 30 MGD point would go to this 85 MGD effluent pump station. The chemically enhanced primary treatment was an important part of the design, even though the wetlands will have, we've basically set them up for good removal of everything that's expected to come into this area, since it is a wet weather facility. We still need to make sure we can remove as many solids and as many things as we could before it got to the wetlands. So this is interesting and a little bit different from a traditional wastewater treatment plant, such that it doesn't have grit removal, and then we're introducing chemicals at this point to get some of those larger solids out. So we are looking at 2 clarifiers, each 130 feet in diameter, both center feeds, and then so combined they would be 115 MGD. Something to note is when we have lower flows, either they'd both be operating, or the diversion structure just upstream would only send flow to one clarifier and not necessarily both. So as part of the testing and the chemicals that were chosen for the clarifiers, I went through a more extensive process than typically done in the planning phase. So we looked at gathering jar tests and samples from each CSO for multiple wet weather events. Those were tested against a set of chemicals that to obtain. And then we were able to go through standard operating protocol, go through extensive testing, and just figure out with the data which made sense, which chemical worked best, and how much would be needed. And it actually happened such that our results showed that our chosen chemical is currently being used at both the east and the west wastewater treatment plants for phosphorus removal. So there would be benefit to using the same chemical as the adjoined east wastewater treatment plant. Here's an example of 2 of the samples that were taken at some of the CSOs. So we were taking basically the CSO 1, 2, and 4. We looked at ammonia, nitrogen, BOD, COD, total phosphorus, and TSS for all 3 CSOs. So next is the vertical flow wetlands. The clarifiers would discharge directly to these wetlands. Here's a bird's eye view of what it would potentially look like. So again, we had planned for 59 million gallons of storage. Most of this would be below grade. So this was that subsurface vertical flow that Daria talked about. A lot of the gravel would be storage area for the water, but it wouldn't technically be above the surface. You can see in this area that there's quite a few sections of the wetlands, and just easier for maintenance and to maintain. Something quite easy to know, the red and the blue lines, the red is the manifold system of the influent. So east to west, you have that larger header, and then about north to south, you have a lot of those lakes coming off the header that have those perforated pipes. And then the blue at the bottom shows the example of the affluent header. And then the lakes coming off that manifold north to south are also perforated. And you can see highlighted in the yellow, you have like the major walkways. That's easy for pedestrians and maintenance to be able to access even when the 59 million gallons is full and the storage is at its highest level. But then the smaller walkways that you see, mostly east to west, some north to south, those minor walkways would be submerged potentially 3 to 4 times per year because they would set lower in elevation. So from there, once water comes in through the header and the lakes of the manifold system, and then get to the effluent lakes and manifold, they go down to the effluent pump station, which pumps to the UV to be sent out to Bee Slough. So here's an example wetland section. On the left, you can see there's multiple layers of washed gravel, and then there is a 24-inch layer of compacted clay at the bottom. And then on the right side, you can see one example of that walkway or that cross section looks like for the pedestrian or maintenance travel. Here's an example of the planting plan. So the plants would be chosen based off uptake, environment, and aesthetics. And then the plant diversity is also important. So it might be mixed within the 10 sections, but we have quite a few manageable amount of diversity here to make it easy to maintain. In the next few slides, here are some examples of what community benefits this could bring and what this could look like. So here's some examples of wetlands and walkways, how the pedestrians or the public can interact with the wetlands. The idea with that, it would be basically a benefit to the community. It would make a popular site to come to for things such as like performances, lectures, maybe like guided tours. There's also a new pump station located pretty close to this site that also provides recreational amenities and education, as well as opportunities for the public to access. So that would be great to have 2 facilities this close together that provide educational opportunities to the public. Some of the examples you'll see here coming up are either like a landmark tower or a bird blind. This is located off Veterans Memorial Parkway, which is a large thoroughfare through Evansville. It's one of the main entrances to Evansville to get from one of the main interstates in Indiana down to downtown Evansville. So to be able just to welcome people into Evansville is a good idea, as well as being able to get more of that environment observation here. Another idea that was considered that would be, that hasn't been shown on the site plan, is an amphitheater along the area. They plan on having educational signage to interpret the site's features through these panels, and then in combination to draw art elements. It can draw attention to the site. There's also a future walk or future trail that is planning to connect a greenway that is existing just north of the site. So it would draw attention from that trail to Bee Slough. And now I will turn it back to Daria.
Thanks, Amanda. So as part of the, our design, we ensured that we evaluated hydraulically pretty much every step of the process between every different component of the treatment plant. So here you can see going from the UV facility to Bee Slough, which is on the left-hand side there. You can see the yellow line, that's the 100-year flood elevation. So we're discharging at that elevation, and then we make sure that when it gets into Bee Slough, that we're below that, because we had to go under Veteran Memorials Parkway. And as you can see, we actually had to introduce a drop structure just left of the UV facility to allow that to happen. And then looking on the right-hand side there, the green line is just the HGL line going all the way back to the effluent pump station for the wetlands. And then to talk a little bit more about the UV design. So the wetlands were actually designed such that the quality of water exiting the wetlands is higher than the influent requirements into the UV. Our UV has 2 channels to receive the peak capacity from the wetlands. And we actually added a redundant channel to the UV facility to ensure that any future increase in capacity could be handled without the utilities needing to upsize the UV facility. And so the flows will be split equally, both in the influent and on the effluent side of the UV facility. There are slide gates for maintenance purposes and to control the flow going into each channel. And we also have control gears and partial flumes to measure the flows going through each channel. So at the top there, that's the plan view of the UV facility, and the bottom picture shows the elevation profile view. So here you see the final plan of the site area. So with all the pieces designed, we also looked at the constructability of the project, and essentially we proposed to construct the treatment plant into different phases, and all would last anywhere between 8 to 10 years. And then we would also break the site construction into different construction packages, which would allow them to be bid separately. And then this is a process flow diagram of the whole facility, and going from left to right, all of the CSOs come in. So CSO 2 is that the one at the top there, and then you have CSO 1 coming in from the bottom, and then CSO 4 coming in from the left, and then all of the flows kind of coming together in the flow equalization structure. But then we also have piping going to storage as needed. And then out of the equalization structure, you'd have the flows going into either the 30 MGD or the 85 MGD screening structure. And then from there into the 85 MGD at the bottom or the 30 MGD influent pumping station. And then the flows come together in the flow structure there, the flow diversion structure, sorry. And then from there, flows go into the clarifiers, and then from there into the wetlands, and then from the wetlands, it's all pumped out to the UV facility, and then from the UV facility to Bee Slough. And then here you can see a bird's eye view of how the site would look like. And you can see the walkways, like Amanda mentioned. You see the 2 purifiers up at the top. There's the pump station there. And as you can see, the actual treatment facilities are closed in, so there's a fence around them. So for safety purposes, the public would not be able to get in there, but they still have full access of the recreation area around the wetlands. And then this is a street view, just looking at it from the street. And as you can see, it's pretty hard to tell that this is a treatment plant. So designed it to make it such that aesthetically it's pleasing to anyone walking by and going into the facility. And so in conclusion, wetlands are a good tool for treatment of wet weather flows. You do have to make sure that your solids and floatables are addressed prior to sending flows into the wetland treatment, which is why we had the clarifiers, screening. And then these are pretty effective as a treatment method, as they can provide dual benefit for the community as well as for the utility using them. So we will take questions, and thank you so much for watching the webinar.
All right, thank you. Let me see. I think there were a couple questions here in the chat. Let me see here. Was any modeling conducted to determine the pollutant removal capability of the wetlands?
And we also had a teaming partner for the design of the wetlands. So any information or any questions that we can't answer, we can certainly get back to whoever's asking the question. But no, I don't believe the modeling was done. However, several white papers were a consultant for percent removal for each constituent. It was mainly based on percentages and research.
Okay. And how about how many overflows occur at the site per year on average?
I believe we had those numbers on the hydrographs, Amanda. I could be wrong. Looks like about 200 closely.
$200 per year?
Let me actually get back to you on that one.
Yes,
Yeah,
I believe combined, but yeah, we can,
Yeah.
if we get the contact information, we can answer that question after.
Okay. How about, like how long will water stay in that wetland system? Is that days, weeks, hours?
The idea is there would always be some amount of water remaining. All the water would not be pumped out. And since a lot of it is below the top of the gravel, it wouldn't evaporate as quickly. So between the amount of water that we would keep within the wetlands and then the recirculation pump and system, the idea is there would always be some amount of water within the wetlands.
Okay. And is there like an overall cost for this this type of project?
For the entire project?
Yeah, is this being funded by the utility?
It would be, although they would be seeking assistance likely through SRF or getting some kind of interest reduction. but it was just, I believe it was about a hair under 200 million.
Okay. But do you know like how much? I mean, that's a pretty good price tag. Do you know what does that utility generate annually?
I am unsure of that at the moment,
Okay.
but yes, that's some of the reason for the multiple construction packages. And then something else to mention is that some of the wet weather facility could be operational after construction package 3. So you would get some benefit before the whole wet weather facility would be constructed.
And in the presentation, did you say it would take maybe was it 8 to 10 years to construct a facility like this?
Correct.
And some of those pictures, you kind of showed some pictures of some other facilities or what the thing may look like. Are those actual facilities that have already been constructed, or are those look like actual facilities?
These, yes, these are just examples. This has not been constructed, at least here at Bee Slough. But in terms of our site plan, some of that was essentially like 3D drawn. It's not been constructed.
Okay. Very interesting. Let me check the chat box one more time. I'm not seeing any other questions at this time, but like you said, we do have contact information for you guys, so that if others have questions that they come up with at a later time, maybe that could be they could be sent to you and you could answer those for us.
Sure.
But I think that's all I see. No other questions in the chat box. All right. Well, again, thank you very much, Daria and Amanda. Thank you for sharing your knowledge and experience with us. I found this very interesting. I also like to thank everyone in our audience that joined us this afternoon. We hope you've learned and enjoyed and learned a few things from this webinar. Please remember, Raul will be emailing everyone with a link to the presentation, a recording of the webinar, and that ever so important PDH certificate. Our next webinar is scheduled for Thursday, August 10th at noon, and registration information will follow shortly. We hope to see everyone there. But that's it. Thank you very much and have a great day.